Hey, this is Lance from LangChain. I want to share some results that we've recently been working on related to RAG over documents that contain a kind of a mixture of text and tables. The motivation here is that tables are present in a wide range of documents, financial reports, earnings reports, things along those lines, academic papers, white papers, technical manuals. So tables are kind of present all over. And the question is, if I want to do retrieval or reasoning over tables, how best can I actually send these into the context window of an LLM? And there's a few approaches that you can imagine that have been also reported. So one option is, well, we have some LLMs that have very large context windows, up to 100,000 tokens or up to hundreds of pages. We can imagine just taking documents that contain tables and stuffing them in together. So the text as well as tables kind of just are fed in directly. Um, there's also a set of methods that try to perform some kind of targeted table extraction. We'll talk a little bit more about that later on, but the idea here is you actually look at the document, you try to identify table elements, you extract them, you pass those into the LLM in kind of a more targeted way. And the third, which is very common for RAG in general, is you take documents, you split them based on some kind of chunk size, and you pass those chunks into first the vector store with embedding in order to basically make them easily retrievable. And you build an application that can very easily retrieve based on semantic similarity to your question documents, and then you document chunks and you send those into the LLM context window. So option one, just take full documents with tables, stuff them into the context window of a large LLM. Option two, try to extract the tables specifically. Option three, try to take documents, split them up, and then kind of do chunk-based retrieval on chunks that also contain tables. So to evaluate these different options, we built a public Langsmith benchmark. So Langsmith is our platform that allows for tracing, evaluation, and other kinds of like observability, monitoring, and evaluation. And what he did here is we took 4 earnings reports from Datadog, Microsoft, Google, Amazon from Q3 2023. So they're kind of recent, they're kind of some interest, and 2 random white papers. The white papers just contain a mixture of tables and text. And we can see that, in particular, the earnings reports contain lots of interesting tables, and they're typically pretty dense. You can see some examples here of like kind of segment information as well as revenue, operating income from Google on the left here. We built 30 questions from these documents, and Langsmith allows us to basically automate evaluation. So we have all these question answer pairs that we've built, 30 of them, and we have our different approaches for reasoning over these documents, be it chunk-based RAG, long context LLMs. And what we can do is for every question, we can get the kind of chain-generated answer. We can compare that to the ground truth answer. We can kind of see that this happens at stage 3. And then Langsmith has very nice capabilities to compare those results across many runs, debug what's going on, and kind of root cause. So that's kind of the approach. Build a small benchmark, 30 questions, and we're going to take our different approaches for RAG across tables and run an evaluation on this data set. So let's look at stuffing documents into long context LLMs first. What we see here is the y-axis shows you the percentage of questions that are correct, and the x-axis shows you different approaches. So we tested Claude 2.1 and GPT-4 128K. Now, these documents combined were not that big. They're around 36,000 tokens. So they don't go to the full capacity of these models, which are around 100,000, 128,000 tokens, but it's still reasonably large. It's not something you could just stuff into, like, for example, baseline GPT-4, depending on the model you're using, 8K, 32K, it kind of exceeds those typical bounds a bit. So you do need these longer context LLMs for this concatenated set of documents that contain all of our tables. And we can see is you can get decent performance. Now, the nice thing is this is very simple. You do almost no work, and you can get, for example, with GPT-4, 72% correct. It's not bad, especially given these are kind of very dense financial tables. Now, there's been some interesting work. This is from Greg Camerant, that has shown that the ability to factually retrieve information from context of these models depends upon the context length as well as the fact placement depth. And what Greg showed is that, for example, as this is with GPT-4 128K, as the context length gets greater, so like as you're passing a much longer context into these LLMs, there are errors. And he did this by placing a single fact in the sea of context at different locations, and then asking, can you retrieve that? So you can see that there are these issues with retrieval quality with respect to both the length and the placement depth in documents. So that's kind of a thing to flag with these long context approaches. You can see degradation, particularly as your context window gets longer, as the fact placement is more central in the document. So here's our results looking at our documents. So again, our context is around 36,000 tokens. So not huge, but again, not particularly small, not easily fit into into more some of the common LLMs that folks use. And we do see kind of a cluster of failures kind of in the middle of the document. And then this is a heat map. I don't show the color bar here, but this dark indicates there's 3 failures kind of in this region. This is one particular table pertaining to Amazon, where we continually get a number of questions wrong. A few others here. So it would be hard to make strong claims about the impact of placement depth on these errors. More would have to be kind of studied there to really be certain about that. But it is worth noting that if you take documents along these lines, which have very dense tables, you send them to a long context LLM, you can get these retrieval failures that may or may not be easy to understand. They may relate to what Greg showed kind of in depth here. It may depend on the context length that you're passing in, as well as like kind of where they are in the document. We saw that there's a bunch of failures kind of in the middle here, and maybe that's kind of a result that is consistent with some other reports showing you can get these kind of lost in the middle type effects where retrieval kind of gets worse as it enters the middle of the document. But in any case, I think more would have to be really kind of dug into here, but it does show that you can't necessarily expect very high performance by just passing in very large context and hoping to get really, really high quality question answering over tables. So that's kind of observation 1. Now, observation 2 is you can try targeted table extraction methods, and there's a number of them. The main intuition is this is Table Transformer from Microsoft. You try to do some kind of table detection, looking at the document, seeing where the tables are, trying to extract the different columns, rows, and kind of pull these tables out of documents in some kind of structured way. A number of different APIs, Dokugami offers some things for this, Unstructured offers things for this. It's an interesting class of methods. We are actually going to follow up in more detail on evaluations here. We have done some initial rounds of evaluation, and one of the things I can flag currently is that these methods have a high ceiling, most likely. It's very promising to think about the ability to detect tables, pull them out, particularly for really complex tables. In practice, what we did see is that because tables represented in many different ways in different documents, consistency of extraction is a challenge. So, for example, one thing we saw in particular is that this is one of the example tables from the Amazon document. We saw that some of these methods actually failed to grab the header columns, and so none of the questions could be answered correctly because the LLM did not receive these headers, so it didn't know how to reason about this information. So In any case, I think the intuition here is that table extraction methods are absolutely interesting to consider. They require like kind of more sophisticated methods. They may be trickier, and they may suffer from failure modes due to the diversity of table representations that you actually encounter in real world documents. So we're going to have more evaluations on this. We're doing some work with Unstructured as well as Dokugami um, on these topics. And so we will provide some more evaluations here in the future, but I want to just kind of give a flavor that these methods have a pretty high ceiling, but there's also some challenges related to the kind of the diversity of kind of table representation that you might see in real world documents. So we kind of wanted to move ahead to chunking. Now, chunking is something that a lot of people are pretty familiar with. It's been very common in RAG to take documents and chunk them up because context windows are limited. You can't just send all your documents into an LLM at once for many cases. And so this idea of chunking and then retrieving chunks based on semantic similarity to a question is like a very popular, appealing approach. Now, here's the results. And I'll kind of walk through this in a little bit more detail, but we see an interesting trend here. So we start with a pretty small chunk size, 50 tokens. So, 4 characters per token, maybe 200 characters then roughly here. And you can see performance is really bad. And as you bump up the chunk size, you can see performance gets better and better and better until we get to this page splits, which I'll explain later, and this ensemble thing, which I'll also explain later. But let's kind of zoom in on this 50 token result and kind of get some intuition here. So Greg Cameron also recently put out ChunkViz. It's a really nice kind of UI just for visualization of chunking strategies on different kind of input documents. So I took one of our tables, I inputted here, and then I set the chunk size to 200 characters, which corresponds to 50 tokens, which is our first. And you can see this table gets split up entirely by the chunking approach, which very much explains why you have such poor retrieval results. Because if you take a table and you break it up into different chunks, you're unlikely to retrieve all those chunks and reconstitute them such that the LM can reason about that whole table kind of together. And this is kind of a main intuition for this chunking strategy is we want to try to design chunks such that they retain full tables. Now, of course, this is what we were also trying to do previously with our discussion about table extraction. Table extraction is kind of the probably the most exact highest performance way of doing this, where you actually try to detect tables and isolate them, extract them individually. Chunking, you're trying to kind of guess based on chunk size what is going to capture tables and which is not. And that's obviously hard to do. We can see in this extreme case, small chunks are very likely to break up nearly all of our tables, and that's a bad thing, of course. But one thing we found, which is kind of very obvious in retrospect, is that in many cases, tables honor the semantic boundaries of pages, which people kind of have used to, improve readability for documents. So, for example, there absolutely are many cases of tables that span many pages, but of course, this does hurt readability for the table. And a lot of documents, at least we are focused on for this initial study, did not contain those kind of multiple page spanning tables. And so the approach here is very simple. If you just build your splits based upon page boundaries, it actually retains your tables pretty well. And so then all you're doing is you're taking a page, embedding that page of text, and then retrieving based upon that embedding, and then sending that particular page to the LM. In practice, this got us 93% accuracy. So quite strong, extremely simple approach. And I completely acknowledge that this will break down in cases of complex tables that span many pages. And it may also break down for other types of complex tables that were not captured in this evaluation set. But I do want to flag that this is an extremely simple approach. We found it to be actually quite performant. And it requires very little specialized engineering, unlike, for example, using some method to extract the tables individually, or even like a longer context LLM, which is kind of not accessible to many people, more expensive. This is very simple. You take your document, you basically embed each page, and then you retrieve pages, pass them to the LLM for final answer summarization, synthesis, those pages typically encapsulate tables pretty effectively, and for many documents, in particular the ones that we covered here. So using these natural page boundaries actually did work really well in practice, just for these kind of simple documents that we are working with. Um, Now there was a problem though. We looked at some of the failures for the approach I just showed. It got up to 93%, but of course there's still some headroom for improvement there. And we saw this. So here was one of the questions that failed. And it failed because it did not retrieve the page with the table. It retrieved a number of other pages that discussed what we were interested in. So the question pertained to the capitalized software development cost for Datadog. And what we found is that particular statement was present in lots of the text chunks outside of the page that contained our table. And so what happened is when we did retrieval based on semantic similarity, a bunch of those text chunks got retrieved and we did not retrieve the table. And so therefore we couldn't answer the question. So a very simple trick that we kind of find in practice worked really well for this is you basically kind of build two different retrievers and you can ensemble the results. And so what I did here was really simple. So I iterate through each page and I built what I call kind of it's using LangChain's multi-vector retriever, but you can think of this as like a table retriever. So what I do is I iterate through each page. For every page of the document, I ask an LLM to tell me, does this page contain a table? If so, summarize it. And if not, just kind of say there's no table present. And what this multi-vector retrieval lets you do is let you index those summaries in a vector store. So you can imagine what we have is a bunch of table summaries that an LLM has generated that link to the corresponding page in the documents. So again, it's like you have a whole bunch of summaries that you've distilled for every page that contains a table. You have all those summaries indexed that are retrievable based on semantic similarity, and then that full raw page, you then can pass to the LLM for answer synthesis. And then of course I combine this with the original just page split vector store and retriever, which we had previously. And with this ensemble retriever, you can actually do something that's kind of nice. You can effectively tell it to prioritize any chunks from one of the two retrievers. So in short, what I ended up doing is I built this table retriever at top that indexed all the different pages that had tables with some table summary. And I combined that with the results of just the general page retrieval. And if there ever is a retrieved document from my table retriever, I put that at the top of the queue in this ensembling. And so what this kind of does is, if there's ever a table relevant to my question, I try to enforce or ensure that we return that because I want to make sure that information is included in the answer synthesis. And when you do this, that's how I got up to 97%. And there still is, I believe, this one question that it's incorrect. And that actually had to do with the need to retrieve documents across a wide range of the different documents and synthesize them. And I'll be following up on that in kind of probably a separate video or notebook that kind of just addresses how to deal with that case. But this was kind of the original set of results that we wanted to share. And kind of in summary, long context LLMs are really nice for getting started. They do fairly well, to be honest. 72% is actually pretty good for effectively, very little effort, just taking these 6 documents and stuffing them in. If you have smaller context, like a single document with tables, that probably works very well. The caveat is there can be these failure modes with respect to both like the context length. So if I try to send in more tokens, like our case it was 36,000. I think as Greg shows in these tables, if you try to push up to over 100,000, you can get this kind of degradation performance. And also depending on where the table is in your context, you could see degradation. There's been reports that in the middle of documents does worse. Greg shows actually there seems to be kind of a lot of failure modes towards the top of the document. So in any case, it's worth more investigation. But the point is that long context LLMs very easy to get started with, have some interesting failure modes with respect to kind of where the table is present in the document. So that's kind of point one. Now, point two is that chunking is also quite easy, very commonly done. The only challenge is you have to ensure that your chunking strategy is not split up tables. It's kind of very obvious. You don't want to break them up because then you can't reason about the information present in the table. And you can see at these smaller chunk sizes, you do certainly break up many of your tables and you reduce your answer quality quite significantly. In short, what we found is just simply splitting on page breaks at least retains for our retrieval set many of the tables and therefore lets you get pretty good performance up to 93%. And a small trick of additional ensembling just to make sure that you always retrieve relevant table chunks if they pertain to the question relative to document chunks um, is a nice way to kind of boost the performance slightly further and ensure that information from tables does get prioritized if it's relevant to your question. And that's really it. I think that was all I had for slides. And we'll be following up a bit more on approaches that involve targeted table extraction in the future. Thanks.